Okay, so I've done a couple videos and we looked at projectile motion, we looked at projectile motion with air drag, and now we want to do something useful with it. So I'm going to show you how to build a program to find the maximum range of a projectile with air drag. Let's get started. So here's a quick reminder. I already did this video. So I have two balls. I throw these two balls. One of them has very small air resistance compared to its gravitational force, and the other one does have a significant air drag compared to its force. So the question is, how do we model the motion of this white ball that is clearly not projectile motion? And oops, I left that on there. So here's our model for, I've already covered this in the previous video. So this is my model for the air drag force right there. So this says that the air drag force is depends on the velocity. It depends on some other parameters like the density of air, the cross-sectional area of the object, and some drag coefficient. And it's a vector in the opposite direction as the velocity. And this is why it's very difficult to model the motion of the ball, because if I say the force changes the velocity, but the force depends on the velocity, then we have a really difficult problem. And we can solve this numerically, and I'm going to show you how to do that. And this is what we did. So again, it's in the previous video, so I'm just going through this fast. So we break the motion into small time steps, and during each one of these time steps, we calculate the force on the object. That's the gravitational force and the air resistance force. And so I know that as a value, as a vector value in that short time interval, and I'm going to assume that force is constant, even though it's not, because the velocity changes. But if I assume it's constant, I can use that constant force to find the momentum at the end of that time interval. Okay, so this is using the momentum principle for a short time interval. And then I can use that momentum to find the new position at the end of that time interval. And then I can update time and repeat this thing over and over and over again forever. And I did that. And here's part of the program just to talk about some of the things. In this program, I have this loop that has these objects. I have a ball object. I'm updating I'm calculating the force here in line 26, and then I have two balls. One has no air resistance, and one does. So ignore 27. And then in 28, I update the momentum, and then 30, I update the position, and then I just do that over and over and over again, and I get this. And so the yellow ball has air drag, and the white ball does not. But other than that, they're identical, and I think that's pretty cool. And there's your final position. Okay, so now in order to to find what angle gives the maximum range, we need to use functions. And I did this backwards, but that's fine. So in Python, functions are a lot like functions in math. It's a chunk of code that does something. You input some values, and it outputs some values. And it actually doesn't even have to do values. I mean, the functions are more powerful than that. But in our mind, we're going to think about it as some code that I give it a number and it returns a number, or more than one number. Okay, and I can input more than one number. So let's look at a couple examples, and then I'll show you how to graph, and then we'll jump right into the actual calculation. Suppose I want to calculate the volume of a three-dimensional box, a cuboid. So it has dimensions length, width, and height. And I can define this function called, and this is the Python code that does that. So I have the function vbox, which I made up that name, and I input parameters length, width, and height. And they could be any values. And then I use those values, length, width, and height, to calculate my volume. And then the key here is to return that value v, and that's what I get right here, okay, in line 5. So a couple of important properties of functions in Python. You want to have this def to define the function. The colon starts the code of the function, and everything that's indented is part of that function. And then return gives back that function. And you don't have to have a return in there, but I could return v, I could return l, I could do a whole bunch of things. And so just as an example, I run the function with values 1, 2, 3, and then I run the function with values 3, 4, 5, and I get an output of 6 cubic meters and 60 cubic meters. So that's just 1 times 2 times 3, and this is 3 times 4 times 5. Okay, so that's a function. And you can call it, right? I could call it with some values in there. Here's another example, one that's a little bit more complicated. This is the arithmetic sum. So if I have some value n, I want to add up 0 to n. Okay, so if I have the value 3, I'd be 1 plus 2 plus 3. And so I want to do that. So I define this, and you have to give it a unique name. I can't give it sum. I think in some modules of Python, sum is already there, so I don't want to use that same thing. I give it some input in, and then that in is going to be used down here. Now you want to be careful about using the same variable as in the rest of your program. It'll probably work out okay, but just be careful about that. So now the first thing I'm going to do is start off with a temp number in that I'm going to use for counting. And there's a better way to do this, but I'm doing it in a simple way. And then the sum, right? Because I'm going to take the value of n, I'm going to increase it and add it to the sum. So in this loop inside the function, I have a while this value temp in is less than that value in. And the first thing I'm going to do is add the temp in value to my sum, and then I'm going to increase temp in by 1. And then I'm going to keep doing that until I get to n, the big N. N. And then I return that. So I'm going to print a sum for n equals 6 and 3. And I get 21 and 6. So that's right, 3, that we can do that. 3 plus 2 plus 1 is 6, so it works. Okay, so there's a loop inside of a function. Okay, one last thing and we can jump into the program. How do you make a graph? Okay, and I've covered this before, but there's really 3 important points to a graph. The first one is to use GlowScript. If you just use plain Python, it's not going to do graphing. Okay, if you use Python and you import something like matplotlib, you can do graphing. But in GlowScript, the graphing is actually a little bit easier. So the first thing in line 3, I have this object called a graph, and I assign it a name, which you don't even have to do, and I give it X title, and I give it a Y title. Those can be whatever you want. I'm going to plot the sum of n for different values of n. The next in line 4, I actually need the curve, the function that I'm going to plot. So here I give it a name f1 for function 1. I don't know why I call that. And I can make the color of the line if I want. Here I'm going to make it blue. So now I have my function from before. I have down here in line 14, I just set n equals to 1. And I'm going to do this up until n is equal to 10. So in line 17, I'm going to plot. This is the other important part of the graph is f1.plot plots one data point x, y, right? Whatever I have. So I want to plot n versus the sum of n. So I can put my function right in there. And I put my value in, which is a number, right? I just put it right in there. And I'm going to plot that data point and then increase my value of n. And then just keep doing that until I get to 10. And here's what I get. 1, 2, 3, 4, 5. Oh, it goes up to, I only did up to, well, it was less than 10, so I only went to 9. And there you go. Okay, so now how do we do this with Python to find the range? Back to finding the range. So here's what we're going to do. Number 1, build a function that calculates the final position of the ball. Now, I'm not going to visualize it like I did before because I don't really care about that. I just want to model the motion by using a numerical calculation in the function. So the function is going to be basically the program I had before. In this function, I'm going to give it an initial velocity and an initial angle. And then we can change that later. But for right now, I just want to change the angle and the velocity. And then it will return the final x position. So I can start with some angle, plot the value of the angle and the value of the range, and then increase the angle and repeat. And just keep doing that and make a graph. And I can see how the range changes as a function of angle. It's going to be awesome. Okay, so these are the same values I had before. I'm going to use these again. The density of air is 1.2. I'm going to use this particular ball right here. Same one as my previous ball. Okay, so let's move over to Python and get started. It's going to be great. I'll see you there. Okay, so I'm actually starting with my old program because why redo everything, right? So if I run this, it should show the 2 balls with air resistance. Yay. Okay, but like I said, I'm gonna destroy this program. So the first thing I want to do is copy it. I'm in trinket.io. I like to use that because it just makes me happy, and then I can change the name of this to air drag max range. Okay, so now I'm going to start destroying stuff. So I don't need the ground. I don't need the ball. I do need the position. I need this initial position. Let's just say r equals vector. Let's just put it at the origin because it doesn't really matter. I do need G, so I can get rid of the ball. Let's move this over. Oh, I do need a graph. Let's put the graph in there. So let's put T graph equals graph. X title equals the launch angle. And let's use degrees, because that's what I like. I don't know why. And then the Y title is going to be the range. Okay, and I need F1 equals G curve, color equals color.blue. The mass of the ball, I'm just going to call this M. I can't give it ball.m if I don't have ball. V0 is fine, theta is fine. Ball.p, I'm just going to call that P. M. V0, everything's fine. Rho, that's fine, fine. I don't need the ball 2 because I don't have no air drag. T equals 0. While, let's do while r.y is greater than or equal to 0, because I don't need to start there. I don't need this rate because I'm not going to plot that anymore. I do need, again, v. Let's just change that to v. I should have just done this all beforehand, but I apologize. Okay. It's kind of fun though, right? Because you can spend some time with me. We can talk about stuff. Fnet. And I'm going to make an error, so that's going to be fun to watch, right? Okay, let's go over here to just v. Gotten rid of the ball. Get rid of the ball. And F2 I don't need because I only have one ball. This is just going to be P. I'm almost done. P. Actually, I'm not almost done. I'm almost done editing this stuff. Ball 2. I don't need that. Ball. I'm going to get rid of this one too. And then ball.pos. This is going to be R. R. P. Get rid of the ball. See, there we're done. Okay, and let's print out this. Just print out the final ball position and the time. It should work. Okay, let's save it. And there's a very, 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 very good chance I made a mistake. Okay, but if it runs, I'll be pretty happy. Oh, okay, looks, I think it's working. Excellent. Okay, so now we need to make a function. Okay, so that's what I'm going to do here. So I'm going to go up. I've already made my graph. I'm going to say def air range. And let's just do drag range because I don't want like the two R's together. And I'm only going to input the initial velocity and the initial angle. So I'm going to say V0 and theta, colon. Okay, so now down here, I don't need to define V0. I'm going to actually cut that out. And I don't need theta. I'm going to cut that out. And so, but now I'm going to put tab, 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 tab. Now notice here, so I don't have a V0 or theta, but I'm using it down here, okay? So I'm going to have to define, when I call it, and I will in just a second, everything's going to work. Tab, 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 tab. I don't remember what my value for theta was. I think I had 35 degrees. So tab. Okay, so now tab. I'm going to return r.x. I'm going to return the x value. And over here, and I'm not going to print r. I'm going to print drag range. And it's I used v0 was 10 and theta was 35 times pi divided by 180. And then I'm going to delete this because I don't have the time. Okay, so now I'm going to, everything's in this function. I'm calling that function. I should get the same thing if I had the same answer, which I don't know. But there you go. It print. I think that worked. Awesome. Okay, so now I don't need that. Now I'm going to go down here to, I don't want to use theta. So I'm going to call this t theta. So I don't want to make a mistake. And I'm going to start this at I don't want to start it at 0 degrees. I'm going to start it at 5 degrees. So 5 times pi divided by 180. And then I need d theta. I'll just call it d theta. And that's going to be what angle should I increase it by? Let's do 2 degrees. 2 times pi divided by 180. And I need v0, so let's call it tv0, and let's put that at 10. I'm not even going to change that. I don't even know what I'm doing. Okay, so now I'm going to say while t theta is less than, I don't want to go to 90 degrees. I want to go, I guess I could go to 90. What the heck, right? So 90 times pi divided by 180. I want to first calculate I want to plot the range. So let's say f1 dot plot my theta value, so it's going to be t theta times 180 divided by pi, because I want to do it in degrees. And then the range, so drag range, and tv0 t theta. That's going to return the x position. I'm going to plot that right there. Now what do I need to do? I need to increase the value of theta. So t theta equals t theta plus d theta. I think that's it. I think that should work, and it may not work. Let's save it because I'm kind of scared right now. I did a lot of weird stuff. If this works, I'm going to give myself a high five, okay? Right in front of the camera. Okay. That was my high five. Good job. Good job, Rhett. Okay. Check that out. So this says that as I increase the launch angle, the maximum range is actually going to be right here at 37.2 degrees, not 45 degrees. Wait, is that legit or not legit? And it goes down to 0, right, when I shoot it straight up. That makes sense. Okay, let's try something out here just to make sure things are working out. If I change this drag coefficient to 0, then there should be no air drag, and the maximum range should be 45. Let's run it and find out. Check that out. Right there. Okay, let's take that back. Let's see. Okay, let me run it. Because, if I make something crazy that I can't verify, I want to do something to see that it's plausible, and that is indeed plausible. So this 37.4 is a maximum range. There's a way you could print out the maximum range, but you can get it from the graph to it, and that's pretty cool. Let's just say 37. What if I increase the velocity to 20? Does that change the angle for the maximum range? Looks like it does, right? Now I'm over here at 32. Okay. Now, what if I shoot at a very, very low speed? It should get back up to close to 45-degree angle, right? Because then the air drag doesn't matter. Let's just go up here and say V0 equals 2. Yeah. Oh, so look, that's pretty cool. Huh. I think what's happening is that it's such a short range that sometimes it like goes below the axis. But you can see it's pretty jagged here because that's a 2-degree jump. And why did that 2 degrees? Because each one of these calculations is already a loop of calculations. And I don't want to, if I make a really, really, really small degree step, which I can do now, let's do that. Let's make d theta equal to 1. Let's do 0.5, whatever, right? I'm going to live dangerously. Let's see what happens here. Okay, so again, you get this jagged stuff, and I think that's really just an artifact of the way the calculations is done. But it's pretty cool. I'm pretty cool. Let's change that up to 20. It'll be nice and smooth. There you go. Okay, so you see how we use functions to model something and determine the answer to something that is really difficult to solve. Okay. I'll include the link down below. I'll also include the previous projectile motion problems. You're not going to learn this stuff without playing with it. I know it went kind of fast, but it's a video. You can play it in slow motion, whatever. So, all right. I'll talk to you guys later.